Hello everyone, this is Uday and welcome to Uday Lectures. In this video, we will discuss about AVL tree and also the properties of AVL tree and different rotation operations that are performed in AVL tree. We will also look into the rotation operations clearly by considering some examples and when the rotation operation should be performed and how the rotation operations should be performed. In an AVL tree, rotation operations are very important and rotations are the only factor which is used for balancing the binary search tree, which we call as AVL tree also. So let us go ahead and understand them. Now, AVL tree is called a self-balancing binary search tree. Why we call this as a self-balancing binary search tree is because a binary search tree can also be a skewed binary search tree. So in that case, we will end up with a worst case scenario in search operation where we will end up having a big O of n as worst case time complexity. So to get rid of that problem, we are trying to balance the binary search tree, and this balancing binary search tree we call as AVL tree, and it is named after the developers of AVL tree. So the AVL tree was developed by Adelson, Walsky, and Landis in 1962. It uses balance factor to balance the height of the tree. And what balance factor actually is? So it is calculated as height of left subtree minus height of right subtree. So if you are not very sure what actually height is and how we calculate height, do not worry, I'll explain them in detail, right? And balance factor is the crucial part in AVL tree, so which will determine the balancing factor, or which will determine whether the tree is balanced or not. And only based on the balance factor we will be performing rotation operations. So it is important to understand balance factor. It is nothing but height of left subtree minus height of right subtree, and different rotations are performed to balance the AVL tree, so which I said already. So first we will construct the binary search tree, and if we get to know that the balance factors are impacted, then we will try performing the rotation operations. Now we will look into your now we will see how a AVL tree would actually look like. So if you see, this is the AVL tree, but this is looking very similar to the binary search tree, of course. So AVL tree is also a binary search tree, only with an extension. So if you see here, I have constructed a binary search tree like this. And if you see that we have balance factors for every single node. So the balance factor for this particular node, which is root node, is 0. So how we computed this is, so height of left subtree. So what actually height of left subtree mean? So the deepest leaf node in the left subtree. So this is left, this is complete left subtree, and the deepest child node, or the deepest leaf node, is considered to calculate the height. So for example, the deepest leaf node here is 5 or 15. So if you look into the number of nodes or number of levels to root node is nothing but height. So if you see from 5 to root node, there are two different edges. So the number of edges also can be considered, and there are two number of edges to root node from the deepest leaf node. So the height of left subtree became 2. Whereas coming to the right subtree, so the deepest leaf node is 30. And from 30 to root node, the number of edges are 2. So the height of right subtree is 2. So coming to the balance factor, so which is balance factor is equals to, so height of left subtree, which is 2, and height of right subtree, which is 2. So 2 minus 2 becomes 0. So that is why the balance factor of this root node is 0. And if you come to this node, again the height of left subtree is 1 and height of right subtree is 1. So which will end up with 0. And it is important to note that, so all the leaf nodes in the tree will have a balance factor of 0. If you see, the balance factors for them are 0. And coming to this node here, you can see the balance factor is -1. How we computed here is that, so for 20, there is no any left child. So where the height of left subtree will be 0. And whereas height of right subtree, we have one node in the right subtree. So the height of right subtree becomes 1. So which will end up with -1. That is why the balance factor is -1. So what exactly the balance factor, and what is the allowed range for balance factor is that, so it is from -1 0 or plus 1. So this is the valid range for balance factor. So if the balance factor of any given node is not within the range of -1 to +1, then we will say that that tree is not balanced and it is not a valid AVL tree. Now we will look into the properties of AVL tree. So the properties of AVL tree are this. So all the rules of binary search tree must be satisfied. If any of the tree is not satisfying the binary search tree rules or properties, but it is having all the balance factors within the range, still it is called a invalid AVL tree. I'm sorry, this is not AVL tree. I'm sorry, this is AVL tree. So properties of AVL tree. Okay. So the balance factor must be in range of -1, 0 or 1. So which I've explained already. And if balance factors of all the nodes will be recalculated for every single change in AVL tree. So if any change, like say you have inserted a node or you have deleted a node from the binary search tree or AVL tree, then we have to recompute the balance factors for all the nodes. So here you can see that I have this particular tree. This is AVL tree again. So we have an AVL tree here. And here you can see that the balance factors are all within the range of -1, 0 or +1. Since the balance factors are within the range of -1, 0 or +1, that is why we say that this is a balanced AVL tree, or this is a AVL tree or valid AVL tree. Now we will look into an example of invalid AVL tree. Again, this is AVL tree. Okay. So this is an invalid AVL tree. Why we say that this tree is an invalid AVL tree? Because of this. So here if you look into the properties, so all the properties of binary search tree are satisfied. That the smaller elements are in the left side and the bigger values are in the right side, and all this and every node is having only two childs and not more than two childs. All these rules were uh, satisfied. But still, if you look into the balance factors, they are not balanced. They are not within the range of -1 to 0 or +1. And that is why we say that this tree is not a valid AVL tree. Even though it is a valid binary search tree, but it is not a valid AVL tree. So what we do in this case, we will try balancing this particular tree to convert this invalid AVL tree into valid AVL tree. That we will see in the next slide. Hope you understood the properties of AVL tree. It has to follow the rules of BST. The balance factors must be within the range, and also the balance factors are recomputed for every single change we perform in AVL tree. Now we will see different rotations that we perform in AVL tree. So in AVL tree, the balance factors are the key factors. So if the balance factors are impacted or they are not within the range of -1 to +1, then we have to perform the required rotations. So the rotations goes like this. So there are four rotations in AVL tree. The first rotation is left rotation, and then the second one is right rotation, and then left right rotation and right left rotation. These two are combinational rotations where we will end up with two rotations, whereas this are only a single rotations. Okay, where we will do only one rotation. We will discuss about this rotation operations in detail one by one with example. So if you look into the left rotation, so the left rotation is performed in this scenario. So the left rotation is performed when tree is unbalanced, when the tree is unbalanced by inserting or deleting a right child. So when we insert a right child in the right subtree, and because of we inserting a right child in right subtree, the tree went unbalanced, or the balance factors were impacted, or they are not within the range of -1 to +1. In that situation, we will be performing left rotation. Now let me explain this with an example. If you consider this tree here, let us say I have recently inserted this particular node, which is 40. Now if you look into this, so the tree, the 40, after inserting 40, the balance factors were impacted for this node. You see, the balance factor of this node is -2. And I have already explained how we calculate the balance factors for every single node uh, in this same video. So just watch that carefully and then you can get back into this place. So the balance factor for this node is minus 2. And since this is minus 2 and this tree is called as invalid AVL tree. So what should we do now? We should perform rotation operations to balance this tree. So here the 40 is inserted as right child of right subtree, right? And that is why we will be performing a left rotation. So this we call as left rotation because we are trying to push 20 to the left side where the balance factor is impacted. And do remember, this left rotation is always performed only between grandparent, parent, and child. So the left rotation must be performed only between these nodes. So we cannot perform the left rotation between, we will be performing only between this because this is the child node which is inserted, and because of this the balance factor is impacted right here. We cannot consider 19 also for this rotation operation because the grandparent of 40 is 20 and it is not 19, and that is why we will be performing left rotation only between these two or between these three nodes. So in left rotation the changes will be this. So in left rotation, this 30, the intermediate node between grandparent and child, which is parent node, will become the root node, and then 20 will become the left child of 30 and 40 stays as right child. And this is how the tree is going to be changed. Now let me just construct this updated tree. So 19 stays as it is because we are not performing anything on 19, and we are performing rotation only between 20, 30 and 40. And in this left rotation, the parent node which is 30 becomes the root node now, and 20, the present grandparent, will become the left child of 30, and 40 will be as it is in the same position. This is how the left rotation will update the tree. And now this nodes will stay as it is because we are not performing any rotations on them. So no changes are made for them. Since we have made some changes into this binaries, into this tree, we have to recompute the balance factors for all the nodes. So we'll start from the leaf nodes, and for leaf nodes the balance factors will be 0 all the time. Whereas coming to 30, so the left side it is one node and right side it is one node, so 1 minus 1 becomes 0. And for this also 0 because left side 1 and right side 1. And coming to this, we have the deepest child as 5 and 15 or 5 or 15. So there are two edges from the deepest child node to 19. So the left side it is 1, 2, and right side also it is 2. So 2 minus 2 becomes 0. So this is how left rotation is performed, and after we perform left rotation we have to check if the balance factors are within the range or not. And here the balance factors are within the range for all the nodes. So now we are done with left rotation and balancing the tree. So this was invalid AVL tree, but now this became the valid AVL tree after performing rotation. Hope you understood left rotation. Now we will see what right rotation would do for the AVL tree and when we should do right rotation. So here, so let us consider this tree, and right rotation is performed in this case. So if we insert a left child to left subtree, which is opposite to the left rotation. If we insert left child to the left subtree, and because of we inserting left child to the left subtree, the tree went unbalanced. So here if you see in this example, let us say I have inserted 2. So 2 is inserted as left child to the left subtree of 10. So since we have inserted left child to left subtree, the balance factor of this node became unbalanced or not in the range of -1 to +1. And that is why we will end up performing right rotation. So right rotation would look something like this. Okay. And here if you see closely, the balance factor of this node is also impacted. But always remember, the rotation operations are performed from bottom to the top. So even though in the top hierarchy there are many nodes with uh, invalid balance factors, still we will be performing rotations from the bottom side. So here in this example, we have to perform rotation operation between these nodes first. And after performing rotation for this, if still the balance factors are not intact to the higher level nodes, then we will end up performing rotations again for them. Okay, so first we will perform rotation for this. All right, listen. If the insertion operations follows the binary search tree properties and the binary search tree steps for performing insertion operation, if you don't know how binary search tree insertion works, please do watch that video. I have already made a video for binary search tree and binary search tree insertion operation, deletion operation, search operation. If you missed that video, please do watch that video first, and then you can come back to this video for better understanding. It is really important to understand binary search tree before we get into AVL tree, because AVL tree is an extension of binary search tree. Alright, now we'll get back to this topic. So here if you see we are performing right rotation. So in this case 5 becomes root node, 5 will jump to the position of 10, and 10 is connected as right child of 5, and 2 is connected as it is in the same place. So now in this case 5 becomes our root node and 10 becomes right child and 2 becomes left child. So this is how we perform right rotation. And always remember, in right rotation also the rotation is performed between grandparent, parent and child. This is really important. Okay, so here in this case grandparent is 10, parent is 5 and child is 2. So this is how the rotation operation is performed, or the right rotation operation is performed. And the very shortcut for this is that in left rotation or right rotation, we will be changing the position of grandparent and parent only. Okay, remember this. So now since we have performed rotation and the changes were made, we have to calculate the balance factors. And balance factors for leaf nodes will be zeros, and for this node it is 1 minus 1 0, and for this it is 2 minus 1, which is 1. So why 2 minus 1? The deepest child node is 2 or 10, and the number of edges between the deepest child node and the root node is 2 edges, so 2, and in right side it is only 1, so 2 minus 1 becomes minus 1. Okay, so this is how the balance factors are computed. And if you see now, the balance factors are within the range of minus 1 0 or plus 1, and now we don't have to perform any more rotations. If you see here, just by performing rotation for this particular subtree, the balance factor of this node also updated, and it is within the range, so we are happy now. Now we will discuss about left right rotation. So it is a combinational rotation. So many of my students and also me confuses sometime in this left right rotation or right left rotation, so it is really important to understand this carefully. So now since this is a left right rotation, it is called a combinational rotation. So how we perform LR rotation is that, so first we perform left rotation followed by right rotation. Do remember that balance factors are computed only after completing both the rotations. So we should not compute balance factors immediately after performing left rotation in the tree. And when should we perform this? It is performed when we insert a right child in the left subtree. So let us say I have inserted a right child in the left subtree, and because of which the balance factors are impacted. And then we perform this left right rotation. Let me take an example for this. So here if you see this tree, I have, let us say we have inserted 8 into this particular tree recently. So after we perform insertion operation, which is 8, which is as a right child to the left subtree of 10. So this is when we perform the left right rotation. Here if you see, by performing 8 as insertion, we got the balance factors impacted for this node and also for this node. And now we have to perform rotation for this particular subtree. Always do remember, the rotations are performed from the bottom to the top. So wherever the balance factors are impacted. If the balance factors are not impacted, uh, let us say I have inserted 8 here, but the balance factor for 10 is not impacted, but the balance factor of this is impacted. Then you perform rotation only for this particular subtree, but not for this tree. So we will be performing rotation for that subtree where the balance factors are impacted. If the balance factors are not impacted, then we will not be performing rotation for that particular subtree. Okay. So now we end up in left right rotation situation. So here how we perform left right rotation is, so we have to perform rotation in two steps. So the first rotation, which is left rotation, so the left rotation is performed between child node and parent node. So whereas in left rotation or right rotation, we perform rotation only between parent and the grandparent. But here it is different. So first we have to perform left rotation, and that rotation will be between child node and parent node. So after we perform left rotation, the grandparent, parent and child will be aligned in this particular way. All right. So if you see, grandparent would be here, parent would be here, and child would be here. So our agenda is to get them in this straight line. And after we perform left rotation, now we have to perform right rotation immediately. Okay. So the right rotation is now performed between parent node and grandparent node. This you remember. Okay. So the left right rotation is a combination rotation where it is performed left rotation first followed by right rotation. The left rotation is performed between child node and the parent node, and then followed by right rotation, which is performed between parent node and the grandparent node. So this is where the nodes will be like this, which exactly the required position for the tree that we want. So now we will first perform right rotation between this particular nodes, so which is child node and parent node. So the rotation that we are going to the rotation that we are going to perform is left rotation. My apologies. So the first we have to perform left rotation. Okay. So after performing this rotation, so the tree would change into this. So 19 stays as it is, 10 stays as it is, and now, so we have performed a left rotation between 5 and 8. What is left rotation? We will try and push the parent node to the left side. So the child node becomes parent, and the present node, the parent node becomes left side. Since we are pushing a node to the left side, that is why we call that as left rotation. Okay, if you are pushing something to the left side, we call that as left rotation. If you are pushing something to the right side, that is when we call that as right rotation. So as we have completed left rotation, now you see that this particular grandparent, parent and child nodes are in this particular alignment, which exactly the requirement of left rotation in left right rotation. Okay, now let me consider this node also. Now as we completed left rotation, now we have to complete right rotation now. So why we call this as right rotation? Because we are trying to push this node to the right side, and that is why we call that as right rotation. So now after performing right rotation, the tree would change into this. So I told you already the right rotation should be performed between parent and grandparent. So here the present parent is 8 and the grandparent is 10. So 10 is pushed to the right side because it is a right rotation. And the present left node will stay as it is, and this node also stays as it is. Now we have completed both the rotations, which is left rotation and followed by the right rotation. And now we have to compute the balance factors. The balance factors for leaf nodes will be zeros, and for this it is 1 minus 1, so it is 0. For this it is 2 minus 1, it is 1. Okay, hope you understood left right rotation. So it is a combinational rotation. First we perform left rotation between child and parent, and then the right rotation between parent and grandparent, and then we compute the balance factors. So here the balance factors are within the range of -1, 0 and +1, and so we call this as a perfect AVL tree or a balanced AVL tree. Now we will understand the next rotation, which is right left rotation, which is opposite to left right rotation. So here first we perform right rotation and then followed by the left rotation. Okay. Yeah. So it is performed when tree is unbalanced by inserting a left child in the right subtree. So if the tree is unbalanced because of we inserting a left child to the right subtree, that is when we perform this right left rotation. Okay. So here if you take this example, so let us say I have inserted 27 recently, which is a left child of right child to 24, right subtree to 24. This is where the right left rotation will come into picture. Because of inserting 27, the balance factor for this node is impacted, and that is why we should be performing rotation between this particular subtree. Okay. So now similar to the left right rotation, it is also a combination rotation. First we end up performing a right rotation between child node and parent node, and then we will perform a left rotation between parent and grandparent. Okay, first we perform right rotation and then we perform left rotation. After performing right rotation, the grandparent, parent and child node should be aligned in this particular fashion. Okay, so and then we will perform left rotation to get them into this structure. Okay, now we will perform the rotations. So first we have to perform a right rotation between this. We are trying to push 30 to the right side, and that is why we call this as right rotation. Let us write the updated tree. So the tree would be updated into this. Okay, so 24 will stay as it is because we are not performing any rotation for that. 21 also stays as it is, but now 30 is pushed to the right side, so 27 will become the new parent and 30 will become the child node. We are not done with the rotation yet. We are left with the left rotation. Now we have to perform the left rotation. So in left rotation, we are trying to push a node to the left side. So here the left rotation must be performed between parent and the grandparent. What is the parent node now? 27 and grandparent is 24. Now the rotation is performed, and after rotation operation, it will be looking into this. So 24 is pushed to the left side. So 27 will become the new parent now, and 30 will stay as it is. 24 is pushed to the left side, and whatever node connected to 24, which is 21, will still be connected as it is, and 19 is having a left subtree which is 10 and 5, that also stays as it is. Now we have completed both the rotations, which is right rotation first and then the left rotation. Now we have to compute the balance factors, zeros for all the leaf nodes, and for this it is 1 minus 0, which is 1. For this it is 2 minus 1, which is 1, and for this it is 1 minus 0, which is 1, and for this it is 2 minus 3. Why 3? The deepest leaf node is 21 and the number of edges between deepest leaf node and the root node is 3, and that is why it is 3. So it is 2 minus 3. 2 minus 3 becomes minus 1. So now if you see, the balance factors are within the range of minus 1, 0 and plus 1, and that is when we call this as balanced AVL tree or valid AVL tree. Hope you have understood this rotation operations and also AVL tree. And if you have any doubts, feel free to mention that in the comment section. If you like the content of this video, please do like this video so that it will be recommended to others also. And if you feel this video is worth of sharing with your friends, feel free to share this video with your friends. And also subscribe to this channel so that you will be notified with all the videos that I upload on data structure problems and different programming languages like Python, Java, and also some development like web development and mobile application development. So if you like the content, do share this and also like this video. Thank you so much. Have a wonderful day ahead. Thank you.